Greetings to everyone. It is my pleasure to present this work on a hardware platform for exploring predictable cache coherence protocols for real-time multicores. I am Zhuanhao. This work was done with my colleagues and my supervisor, Professor Hiren Patel at the University of Waterloo in Canada. Safety-critical system applications in avionics and automotive domains are pushed towards using multi-core platforms due to their cost and performance benefits. Multi-core computing platforms consolidate multiple processing units onto a single component, resulting in enhanced application performance and reduced power consumption. In this work, we are focusing on the cache-based multi-core platforms, where the memory hierarchy consists of multiple levels of caches, where some of these levels are private to cores and some are shared across cores. In this setup, caches hold a subset of data stored in the shared main memory. Evidence of shared data communication in real-world safety-critical system applications has been shown in research, and it prompted the research efforts in predictable data communication among cores on real-time multi-core platforms, among which the predictable hardware cache coherence is an attractive solution that provides worst-case latency guarantees as well as an advantage of average case performance over other state-of-the-art predictable data communication schemes, such as cache bypassing, data duplication, and task collocation. When designing the predictable cache coherence mechanism, the designer constructs the protocol state machine and conceives microarchitectural details as a first step. Next, the designer creates the prototype for the proposed mechanism, and after that, the designer conducts worst-case timing analysis. And finally, the proposed mechanism is evaluated. Prior works on predictable cache coherence mechanisms rely on microarchitectural simulators such as Germ5 to perform prototyping, analysis, and evaluation. While microarchitectural simulators are good for fast design space exploration, they may not fully model the details, which results in imprecise timing analysis. Our work, MapleBoard, focuses on hardware prototyping with Chisel. As a result, MapleBoard can benefit from the Chisel ecosystem, as well as allowing the designer to perform fast design space exploration. Also, MapleBoard achieves accurate and precise timing analysis since it takes into account hardware details. Our main contribution of this work is the MapleBoard. MapleBoard includes a real-time multi-core hardware platform that integrates the cache coherence mechanisms. It also includes tools for fast design space exploration for cache coherence mechanisms, one of which being a domain-specific language for specifying cache coherence protocols. The multi-core hardware platform can also be synthesized to Xilinx VCU 1525 FPGA board. MapleBoard is open sourced on GitHub. The remaining talk is organized as follows. We first briefly introduce background for cache coherence, then we present MapleBoard and its components. After that, we present our case study done with MapleBoard, showing an alternative to the bus configurations used in prior works, where our proposal features a worst-case latency that is linear to the number of cores. We then back the case study with our evaluation, and finally we reach our conclusion. Hardware cache coherence is a data communication mechanism that enables cores in a system to simultaneously cache and access data in their caches, while maintaining a coherent wheel of the data across all cores. Cache coherence protocol plays a central role in guaranteeing a coherent wheel of data. Below is an example of the MSI cache coherence protocol. A cache coherence protocol defines a set of coherence states and a set of state transitions among them. The cache coherence states capture the access permissions of data, whether it is read or write. The M stands for modified state. A cache line in this state can be read or written. The S stands for shared state. A cache line in this state is read-only. And I stands for invalid. A cache line in this state is invalid or not cached. In this work, we focus on the cache coherence mechanism deployed in Snooping Bus. In a Snooping Bus setup, when a core issues a request, all cores including the requesting core itself can observe the request on the bus and react accordingly. Snooping Bus is an attractive option for real-time multi-core systems due to the limited number of cores in such systems. Then, we introduced the MapleBoard, a real-time multi-core hardware platform for cache coherence mechanisms which is capable of synthesizing coherence protocols described in MapleDSL. The design flow of MapleBoard is as follows. First, the designer describes microarchitectural extensions of the multicore platform in Chisel and advises coherence protocols in MapleDSL. Next, the designer can generate a Verilog design and perform full system simulation with the Verilog simulator. After that, the designer can use FPGA synthesis tools to generate logic for the extended multicore architecture. And then, the designer can execute software applications in C or C++, compiled as binary to be executed on the FPGA. Next, we introduce each component in MapleBoard in detail. The MapleBoard hardware includes a core architecture that implements the RV64IA RISC-V ISA. MapleBoard has a two-level memory hierarchy. Each core has a private data cache and private instruction cache. Cores are connected to the shared real-time bus. The bus is then connected to the shared memory. The private cache in each core is bi-digestible with 64-byte cache lines and has configurable weight and size. The private cache controller also includes pending writeback buffer, PWB, and pending request buffer, or PR, to support predictable cache coherence mechanisms. The PWB queues up writeback requests, and PR stores the request for data. Predictable arbitration are deployed for PWB and PR to ensure timing predictability as proposed in prior works. We also provide arbitration policies for the snooping bus, such as round-robin, TDM, weighted TDM, and a combination of TDM and round-robin for a mixed criticality multicore system. At the shared memory, we implement the pending request lookup table, or the PRLUT, to order requests from the same address, as suggested by prior works to ensure timing predictability. In MapleBoard, we support system calls, making the execution of pthread programs possible. The support for system call is divided into two parts. The first part is for supporting pthread-related functions and memory management, and is linked against the program. These system calls are emulated within the course. Examples include fork and mmap system calls. The second part, such as open and read system calls, relies on a host running Linux OS. When a program encounters such system calls, the system calls are delegated to the host system. Note that when hosts communicate data with cores, the request from the host is also serviced with the same predictable cache as the cores. Another important feature in MapleBoard is MapleDSL, a domain-specific language for describing cache coherence protocols. The MapleDSL allows the designer to specify predictable cache coherence protocols as well as conventional cache coherence protocols. The compiler flow for MapleDSL is as follows. The designer specifies the state transitions in MapleDSL. As part of the process of compiling the Chisel code into synthesizable RTL, the MapleDSL converts the coherence protocols into a coherence table, which consists of a list of condition checks and signal drivers. After that, the coherence table is converted into a combinational logic and integrated into the cache controller. We provide an example on how MapleDSL can model the transition of a cache line from invalid state to modified state in a system with a snooping bus and TDM arbitration. When the core attempts to store data to a cache line in invalid state, it is a cache miss, and thus the cache controller needs to get the data from the shared memory before the core can write to it. A state transition in MapleDSL consists of an event component, which is a tuple of coherence message and coherence state, and an act component, which is a list describing the actions performed by hardware components. To start with, the cache controller observes a store on a cache line in invalid state, or denoted as an event of store on a cache line in I state. The cache line is then transitioned from I state to a transient state IMAD, meaning that the cache line is transitioning from invalid state to modified state, and it is waiting for the request to appear on the bus and also waiting for data. This is denoted by the state IMAD in the act component. Meanwhile, the cache controller inserts the request from core into the MSHR and inserts a getM request into PR. Next, The snooping bus grants it access to the core when it is the core's own TDM slot. When the requesting core observes its getM request on the bus, an onGetM event is fired, and the cache line now only waits for data, denoted as IMD. In a next TDM slot of the core, the data is sent from the shared memory controller through the data bus, triggering a data event. With the data, the cache line is transitioned to the modified state, and the cache controller can respond to the core with the data and update MSHR, PR, and Tegegn data array correspondingly, completing the transition from I to M. We also perform a qualitative evaluation for MapleDSL and use the linef code to show the conciseness of MapleDSL at an abstract level. Our result indicates that when the coherence protocol is specified in MapleDSL, the linef code reduced by more than 90% compared to the linef code in the generated Verilog. MapleDSL exposes the hardware components such as PR and PWB directly to the designer. What's more, the designer can embed relative criticality as part of the state transition clauses as well. These features allow MapleDSL to model complicated criticality-aware coherence protocols such as CARP. Now, we will focus on a case study that makes use of MapleBoard. To highlight the design space exploration utility of MapleBoard, we conduct a case study on exploring bus configurations and their worst-case latency. A snooping bus is composed of a message bus to communicate messages, such as getM, and a data bus to communicate data. In prior works, the message bus and the data bus are shared across all cores, and the access to the bus is exclusive. We name such bus configuration as shared data bus, as is shown on the left. The white channels are for messages, and the black channels are for data. In this case study, we study the dedicated data bus configuration, where each core is equipped with bidirectional data bus that is not shared and does not undergo the arbitration, as is shown on the right. We use an example to show the benefit of dedicated data bus. Consider a system with 3 cores with a snooping bus with TDM arbitration with the schedule on top of the slides. Initially, core 0 holds cache line A in modified state. At time 1, core 1 broadcasts a request to obtain cache line A in its own slot. In shared data bus configuration on the left, because the data bus is shared and the slot is granted to core 1, core 0 cannot write back at time 1 and has to wait for its own slot to come. However, in dedicated data bus configuration on the right, core 0 can write back cache line A as soon as it snoops the request from core 1, highlighted in green. At time 2, the slot is granted to core 2. In the shared data bus configuration on the left, core 0 is still waiting for its slot to write back in an M star state. In the dedicated data bus configuration on the right, core 1 can receive the data through the dedicated data bus and finish the transaction. At time 3, core 0 is granted access to the bus. In the shared data bus configuration, core 0 can finally write back the data. At time 4, core 1 is granted the access. In the shared data bus configuration, the shared memory can send data to core 1, finishing its request. On the other hand, in the dedicated data bus configuration on the right, core 1 has finished its request at the end of time 2. As our example has shown, in shared data bus configuration, a core writing back dirty cache line has to wait until its own slot. Thus, prior works on predictable cache coherence mechanisms achieve worst-case latency that is quadratic to the number of cores. With dedicated data bus configuration, writebacks can be performed immediately through the dedicated data bus when needed. This eliminates the waiting for a responding core's slot, achieving linear worst-case latency with respect to the number of cores. The figure on the right visually shows the worst-case latency bounds versus the number of cores for shared data bus (SDB) and dedicated data bus (DDB). We refer interested readers to the paper for detailed proofs on the worst-case latency in dedicated data bus. Our evaluation covers the worst-case latency and execution time for different core configurations. We conducted the evaluation for 2, 4, 8 cores with a number of cache coherence protocols, but we only show results for 8-core configuration in the slides for predictable MSI protocol. We present the worst-case latency of 8-core configuration in this graph. The x-axis of the graph represents benchmarks from Splash 2. The y-axis represents the observed worst-case latency. In the graph, DDB stands for dedicated data bus and SDB stands for shared data bus. Blue bars represents DDB while orange bars represents SDB. The two horizontal lines are the analytical worst-case latency of bus configurations. As we can see, for 8 cores, the dedicated data bus configuration achieves a lower bound compared to shared data bus configuration. Also, the evaluation shows that the observed worst-case latency are within the analytical bound. Next, we present the total execution time of 8-core configuration in this graph. The x-axis of the graph represents benchmarks from Splash 2, which are executed as compiled RISC-V binaries. The y-axis represents the execution time. Blue bars represents DDB, while orange bars represents SDB. The green bars are the result for MSI protocol for reference. According to the graph, for PMSI, DDB maintains slightly better performance compared to SDB. MSI also performs better than both SDB and DDB. In conclusion, our main contribution in this work is MapleBoard. MapleBoard includes a real-time multi-core hardware platform that integrates the cache coherence mechanisms. It also includes tools for faster design space exploration for cache coherence mechanisms, one of which being a domain-specific language for specifying cache coherence protocols, the MapleDSL. To show the efficacy of MapleBoard, we conduct a case study on exploring bus configurations and worst-case latency. We show that the dedicated data bus configuration can deliver worst-case latency that is linear to the number of cores. MapleBoard is open source on GitHub as well. Thank you.